Okay, so let me start. Vectors, right? So this is one of the fundamental topic for understanding statics, right? So even with the dynamics also, it is very much needed. So first of all, actually, we need to understand what is a vector. Can somebody tell me what is a vector? Okay, so vectors. So this is actually one of the fundamental topic to understand statics, right? So first of all, I just wanted to ask you one question. What is a vector? Why do we need to learn about vectors? So a physical quantity which has both magnitude and direction, right? So how can you identify whether a physical quantity is having a direction and magnitude both? How we can identify that? Suppose if I say that displacement, then actually is it a vector or a scalar? So it's a vector. Suppose if I say mass, right? So you will straight away say that it is a scalar. But what is lacking there? Now actually, suppose actually, I'll just give you a simple information here. See this, suppose if I say that this chalk piece is weighing, let us say the mass of this chalk piece is 10 grams. If I say this, then actually you feel that actually, so the chalk piece mass is 10 grams and you have no questions to ask. Suppose if I say that I push, just if I say that I push, immediately, so you will ask a question saying that in which direction you push, right? That means there is something lacking there. So the completeness of the physical quantity is lacking. So this is complete only if I specify I pushed with a force of 10 newtons in the direction of east. If I say like that, then you say that actually the description of the quantity is complete, right? So this way actually to identify whether a quantity is a scalar or a vector, so you will have to ask the question whether the direction is needed for that physical quantity or not. This is the fundamental thing, right? So to be specific, we can define this vector as a physical quantity whose description is complete. Complete only if both magnitude and direction are specified. Is called a vector. And counter to that, a scalar whose description is complete, a physical quantity whose description is complete only with its magnitude is called a scalar. Right? So this is the difference between the vector and a scalar. Now, examples of vector are displacement, force, velocity, so acceleration, so you can name anything. Now here actually coming to the scalars, mass, distance, density, etc. So these are the scalar quantities. Now actually, where is the fundamental need to describe the physical quantities into vectors and scalars? We are separating it here, right? Why do we need to separate this? Without separating, can't we do? So where is the need to classify the physical quantities into vectors and scalars? Where is the problem coming there? Why do we need to classify that? Can somebody give me the answer? What is the problem if I treat everything as scalars? Without considering the direction, if I say that all the physical quantities, I say that scalars, then actually where is the problem coming? Okay, so let me give an example. Suppose if I say that the mass of this chalk piece is 10 grams and the mass of this chalk piece is 5 grams, then if I add these two together, you say straight away that 15 grams of mass is there for both of these chalk pieces together, right? But if I say that I push with a force of 10 newtons in this direction and I push with a force of 10 newtons in this direction, like this actually I am pushing it. Now what is the effective force? Exactly in opposite direction with the same magnitude actually I am pushing. So this is 10 newtons force, this is 10 newtons force. Both together actually I have applied like this. So the resultant you say that it is 0. But ideally it would have been 10 plus 10, 20, right? Because this 10 and this 5 together I am making as 15. But this 10 and this 10 together I am calling this as 0. That's where the problem comes. So as long as the direction is involved, then actually the normal algebra, whatever we have learned, that will completely fail for all the physical quantities. So whatever the normal algebra we have learned, the addition, subtraction, multiplication and division, so everything will not be working for the vector quantities. That's where the problem coming. So if it is a scalar, straight away you can add like this, 10 plus 5 is equal to 15. So whatever the mathematics we have learned with the addition, subtraction and multiplication and division, that is valid only for the subclass of scalars, not for the vectors. So there is a need for the mathematicians to define something called vector algebra, which will be useful for the calculations of the vectors. So there the solution coming as in the form of vector algebra. So normal algebra is different and vector algebra is different. So in the normal algebra or plain algebra, what it says is 10 plus 10 is equal to 20, but here 10 plus 10 is not equal to 20. So this is where the problem. So there is a need to redefine plus, there is a need to redefine minus, there is a need to redefine multiplication, there is a need to redefine the division, right? So that's what actually we are going to talk, that is the vector algebra. So just note down this. Done? Okay. Now, before proceeding to the vector algebra, so let us classify the types of vectors and the representation of the vectors. So representation of the vectors, right? So a physical quantity, if you wanted that to be identified as a vector, there has to be certain convention. That convention is, so this is the name of the physical quantity. On top of that, you have to put an arrow like this, specifying that this is a vector quantity, where indirectly you are saying that without considering the direction, you cannot do any mathematical calculations for this particular physical quantity. That is the intention of identifying this, right? And then graphically, if you want to identify a vector quantity, so you will draw a line like this and then put an arrow to specify the direction of that physical quantity. And top of that, you specify the magnitude of it and then put a vector quantity like this. So this is the graphical representation of a vector. The length will show the magnitude. Length will show the magnitude and the tip of the arrow will show the direction of the vector. So this is the way actually you represent a vector quantity. For scalars actually you don't need to specify in a line because that is a straight away addition or multiplication or division, right? So this is how actually you will be representing. Now different kinds of vectors. There are actually multiple ways actually we can classify these vectors like equal vectors, parallel vectors, anti-parallel vectors. So such kind of vectors actually you can define, but all those things are not needed. These are very, very fundamental. So some of the important types of vectors actually we will be discussing it. So in that, one is something called position vector. Unit vector. So unit vector, position vector, and third one is coplanar vectors. So these three forms are very, very important for us. Coplanar vectors. Now, what is a unit vector? What is a unit vector? So a vector whose quantity is equal to 1, right? Whose magnitude is equal to 1. Then why do we need that? We know that the magnitude is anyway 1 and we are saying it's a vector. Then why do there is a need for the unit vector? So only for specifying the direction, that's exactly, right? Only for specifying the direction actually this unit vector needs to be defined. Suppose actually if I say that, so you go in this particular direction. So if actually somebody asks me the route, then actually I say that go in this particular direction. I'm not specifying the magnitude, how much length he needs to travel. I'm just saying that you go in this particular direction. We say just a single statement, go in this direction. That means there actually it is needed to specify only the direction. No need of the magnitude. In such cases, this unit vector is needed. Now, to be specific, this unit vector is very widely used to identify as the position vector, right? So, position vector, so by name as it suggests, right? So, it is used to identify the position. Identify the position of a point. So if I say that a position vector is used to identify the position of a point, then indirectly what I am conveying here it is a must to represent in a coordinate system. A unit vector, so a position vector has to be represented only on the coordinate system. That is the indirect meaning of conveying this, right? So when we are specifying a point, right, so it has to be on some coordinate system. Otherwise actually there is no meaning for that. Suppose if I ask that, where is Hyderabad? Just if I ask that question, right? So where is Hyderabad meaning? So there actually the indirect assumption is that you are in front of me, and then actually what I am asking is from here, if I have to travel to Hyderabad, how do I need to go? Or actually where is located with respect to our position now? So this is how the complete question it will be, right? So but we are asking where is Hyderabad simply. So where is Hyderabad means from this location where is Hyderabad? So there actually indirectly we are specifying that the coordinate system origin is where we are located, and with respect to this location where Hyderabad is located. This is how actually indirectly we are asking. Here exactly the same situation comes. A position vector represents a point on a coordinate system where a coordinate system contains the origin or the starting point always, right? So if I put it in the Cartesian coordinate system like this is x-axis and this is y-axis. And then actually, if I locate this particular location, let us say this is Hyderabad and this is the position where we are standing, then actually with respect to this particular point, this is located at this location, right? So this is how actually you can represent the position vector now as the starting point to the ending point like this. This is the position vector. With respect to this origin, this is positioned at this particular point. Hence, we call this vector as a position vector. This is a position vector. Now, to reach that point, right? So you may select different ways. Suppose if I travel in this particular direction and in this direction, now actually I traveled in this direction as x and till this particular point for a distance of y, then this vector, so this is traveling in the x direction for x and y direction for y. Total actually you will be reaching this particular location, which is the vector sum of this xi and yj. Now here actually, let us say this is a r vector, which is nothing but the position vector. R is equal to xi plus yj. Now here actually, there is a need to identify the direction here. So this is the unit vector in the direction of x and this is the unit vector in the direction of y. So earlier actually I have explained what is a unit vector. Here exactly the need. Now actually to identify this location, I have to explain in this manner. You travel along the x direction for a distance of x. So there actually there is a statement involved. You travel along the direction of x. So that statement is completely replaced by a single letter called I. For a distance of x, which is nothing but the magnitude. That's why xi will represent with a magnitude of x travel in the direction of x. So that is I. Similarly, in the direction of y has to be replaced with j. This is a universal convention for a magnitude of y. So yj. These two together will make you to reach starting from this location to this location. So that is how actually you will be representing a position vector in Cartesian coordinate system. Now coming to the position vector, right? So the way you represent or the way you talk about the position vector, that depends on the type of coordinate system you are going to use it. If it is a Cartesian coordinate system, you will be representing in this particular manner. But if it is in a polar coordinate system, then actually you will be specifying the angle theta and the magnitude of r like this, right? So this is how actually you will be representing it. Now that's exactly the reason. So why actually this position vector is dependent on the coordinate system, right? Okay. So this is r. Now the magnitude of this particular vector, any vector magnitude, the way you calculate is, suppose if I take this one, modulus of r is equal to x square plus y square under root. So why I am writing this way is, you wanted the length of this particular vector, which is nothing but the magnitude of that particular vector, and this length you will be able to find out with the help of Pythagoras theorem. This length is x and this length is y, and the angle between them is 90 degrees. Obviously the length of r is square root of x square plus y square, which we call as the magnitude, and the direction of the vector is this angle with respect to the x-axis, which is nothing but theta is equal to tan inverse of y by x. This is the magnitude. So here actually unit vector is a must to identify the position vector. Got it? So here the application of the position vector. Got it? Okay. And the third one is the coplanar vectors. Coplanar vectors means the vectors which are on the same plane. So as I explained in the previous class, right? So whatever the vectors we are dealing with in case of statics, right? So 90% of the cases are only the coplanar vectors. Coplanar means co means same, planar means plane. So the vectors which are sharing the same plane are called coplanar vectors. Suppose if I draw three different vectors like this, then all the three vectors are drawn on the board only. That means on the board, this is one vector, this is one vector, and this is one vector. Now all the three vectors are drawn on the board itself. Hence, all these are on the same plane of board. Then we say that these are the coplanar vectors. And the non-coplanar vectors are, suppose these three vectors are on this particular plane. If I say that there is one more vector like this which is coming out of the board, then obviously these four vectors are no more coplanar, because this vector which is coming out of the board, which is perpendicular to the board, not on the board of the, so same plane of the board, right? So that's why these are non-coplanar vectors. So the scenario that are coming here, it is, suppose actually if there are multiple forces acted upon at a single point, and this situation comes especially in the dams and bridges, right? So if there is a iron frames, so that are built. So like this actually, there are supports on the bridge, right? It will be like this. So there will be a load like this. This is one support and this is one support and this is carrying one more, right? So now actually at this particular point actually, all the forces are meeting together. Now there is one force acting from the top. These two are supporting pillars, and these are actually transmitting for the next trusses, right? Now here actually whatever the force we calculated here, right? So it has to be under equilibrium condition, which essentially means that all the forces together makes a resultant of zero, right? Now here the analysis what we are going to deal with here, it is all are coplanar vectors. Coplanar means all are on the board itself, right? So this is one direction, 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 but every direction is only on the board. That's why it is coplanar vector. Suppose if there is one more force like this actually, like chalk piece actually, if it is acting, then actually we say that this is not a coplanar vector, right? So whatever the vectors we are going to deal with is 90% of the cases are only the coplanar vectors. Only in 3D case only, like actually three-dimensional vectors, if you take it, there actually we will be dealing with non-coplanar vectors also. So that is the equilibrium of body under 3D forces. So there is one topic which is the last topic. So there actually you have to divide all the vectors into x direction, y direction and z direction, and then actually try to calculate the equilibrium of that particular body at that location. Fine? Okay. So these are the different kinds of vectors actually what we are going to deal with. So you note down this. And coming to the unit vector, actually let me expand a little better. See this. This is x direction, this is xi, and this is yz. Now actually, here actually, this is also x direction, this is also x direction, this is also x direction. Wherever the direction, so wherever the line you draw, if it is pointing in the direction of x, then actually we say that is a unit vector in the direction of x, as long as the magnitude of the vector is 1. Suppose wherever the vector I draw with a magnitude of 1, which is parallel to the y-axis, then we say that the unit vector is in the direction of y, which is nothing but j. But what if we take the polar coordinate system? The polar coordinate system, so this is a vector. Now polar coordinate system, the horizontal line is called as the initial line. This is initial line, and then from the initial line, it is making an angle of theta, and with a magnitude of r, actually this vector is there. Exactly the same vector, actually I have drawn it here, but in a different coordinate system, what we call as the polar coordinate system. Now the unit vector in the direction of r is nothing but this direction. So this direction vector is r cap. There is a unit vector defined in the r cap direction. The way we define the r cap is going away, starting from the origin. That is how actually we need to be defining. That means here actually the horizontal direction is always x direction. Now actually, what is the unique direction of this particular r cap? Give me one more vector which is equal to r cap. Can somebody give me one more vector which is in the direction of r cap? So r. So this is one vector anyway. So that actually r cap direction. Now actually, if I draw this direction, can I say that this direction also r cap? Can I say that this is also r cap? Yes or no? Yes, right? So even if I draw in this direction, this is also r cap. Even if I draw in this direction, this is also r cap. This is also r cap and this is also r cap. Now actually, if you notice in all the 360 degrees, right? Starting from origin, whatever may be the direction you go, that you treat as r cap direction, which is nothing but the unit vector in the direction of the radius, right? So the theta cap direction, so this is theta cap direction is treated as which is perpendicular to r cap. Now actually if I draw a circle like this, and this is theta cap here, and this is theta cap here, this is theta cap here, and this is theta cap here, and this is theta cap here. So theta cap direction, the way we treat is which is perpendicular to r cap, wherever it is, we treat that as theta cap direction, right? So this is how actually, so don't get confused with that. So the unit vectors actually which are parallel only has to be treated equal. But here actually, though these are non-parallel, still actually all these are r cap direction, and all these tangential vectors are always treated as the theta cap direction, right? Got it? Any questions? Any questions? Yeah, you can note down this. So these are the different kinds of vectors. Done? Okay. And the next one is vector algebra. In the vector algebra, right, all the algebra principles actually we need to be redefined. Now, in that, so the first one is addition of vectors, Because actually all the vectors actually are failing to obey the scalar principles. Addition of vectors, subtraction of the vectors, and third one is multiplication of the vectors. Fourth one is division of the vectors. Right? Now actually, so did you ever heard about the division of the vectors? Did you notice in textbooks where actually the division of the vectors is specified? As we are redefining the addition, subtraction, multiplication and division, right? Did you ever notice division of vectors? Yes or no? No. Then the question is why? So as I said, right, so actually from normal algebra, actually we felt that addition, subtraction, multiplication and division are equally important in all the cases of scalars. Then actually, why there is no need for division in case of vectors, and there are two different kinds of vector multiplication, dot product and the cross product. Now actually why there is a need for the two different kinds of multiplications, and even in the addition of the vectors also, so you will be learning only the addition, but subtraction actually we feel that it is a redundant case, right? So let me explain the addition first, then actually we will discuss one by one. Now the addition of the vectors, right? If there are two different vectors, there are different ways of adding the vectors. So first one is parallelogram law. Parallelogram law of vector addition. So what it says is, here actually, let us say there is a body like this. On this body, if I push this particular body with a force of F1, and if I push with a force of F2, and this F2 is far more than F1. Now, the resultant of this particular two different forces, so resultant we mean these two forces together for this particular body, in which direction actually it will try to move. That's what is nothing but the resultant of these two forces. Now actually, being this is a lesser force, it will push lesser. Being this is a greater force, it will push more in this particular direction. Obviously, this will try to move in this direction and this will try to move in this direction with a lesser amount. The resultant will be, obviously, it has to be like this, right? So this won't go in this way, this won't go in this way, this will straight away move in this particular direction, right? That's what we call this as the resultant of these two vectors. Now here if you notice, indirectly what we have given is, being this is the bigger force, we have given bigger importance. That's why actually this body tries to move in this particular direction more. And still actually it is given certain importance to this depending upon the magnitude of this particular force by moving in this direction. Together actually will try to move. So the vertical distance will be less and the horizontal distance will be more. You have given the importance according to their magnitude along with these directions, right? Now actually, if I put this particular body as like this, more force like this and less force like this. If I do this, then actually lesser movement in this direction, bigger movement in this direction, and the resultant will be, it will try to move in this particular direction. Now actually depending upon the magnitude and direction, actually the resultant will be calculated. Now here actually the parallelogram law indirectly it satisfies, right? Indirectly what we mean here it is, so if you draw a parallel line like this and if you draw a parallel line like this and then join the opposite corners, automatically that will be the resultant force, because this is giving importance both to this length and this length. So from this principle actually parallelogram law of vector addition was invented. Now the parallelogram law of vector addition, what it states is, now actually if there are two different vectors, with a magnitude of P and with a magnitude of Q, then try to complete the parallelogram by drawing the parallel lines with the same magnitude and then join the start point to the end point of the diagonal. So that is from this location to this location. If you join it, obviously this will represent, R will represent the magnitude of the resultant along with its direction. Now this will be the direction here, and even this is also a direction. This direction can be specified with respect to this force, or it may be with respect to this force. That is up to you. How do you want to specify it? Now in this case, as a standard convention, the horizontal force actually usually we are intended to take the horizontal as the reference. Hence, the direction will be specified with respect to the horizontal force, but it may not be a rule. So you can even specify with respect to Q also. Got it? So this is alpha and this is beta. So with respect to P, it is alpha, the direction, resultant direction. With respect to Q, beta is the resultant direction, right? So the length of this particular one, so this will give the resultant magnitude along with the direction. So this is a graphical technique. To find out the resultant of two vectors. To find out the resultant of the two vectors. Now here actually analytically we will be able to find out by completing this triangle like this. By making this as a right angle triangle, then if you are completing this triangle, you know that this is the height and this is the entirely the base. Then actually this hypotenuse length actually you will be able to find out with the help of Pythagoras law. Now here this is the angle theta. This theta, why do we specify is when you wanted to mention any particular force, you have to specify the direction as well. Now initially when we start with a single force, let us say I take this one. This is a block. On this block there is a force P that is acting on this. Now actually there is one more force Q also actually acting on this. Now if you want to specify this with respect to the first force, whatever you have selected, you will have to specify the direction. With respect to this force, I am applying a force of magnitude Q in this particular direction. That direction is nothing but you will be specifying with the help of angle theta, because direction implies angle. Now here actually this is the horizontal and this is how actually you have specified. That means with respect to the horizontal, this is the angle theta. Or actually if you extend these two, this will be the angle theta. Got it? So this angle theta is specified like this, and this is the horizontal force and this is the one more force which is acted upon the same body at an angle of theta. Now if you want to specify the resultant magnitude analytical manner, this length is P, you know, and this is Q cos theta and this is Q sin theta. Because this is a parallelogram, if this is Q and this will also be Q, then if I take this particular triangle here, this angle is theta with respect to this angle is theta because these two are parallel and this value is Q. Then what is this magnitude? The horizontal one. Suppose if I say that ABC, what is the length of AB? What is the length of AB? Q cos theta. How can you say that this is Q cos theta? So if this is X and this is Y, then obviously cos theta is equal to X by Q. Cos theta equal to X by Q, and from there X is equal to Q cos theta. Similarly, sin theta is equal to Y by Q and Y is equal to Q sin theta. So this is how actually you can divide this vector into horizontal component and vertical component. This is what is called the horizontal component and this is what is called as the vertical component. Now this is Q sin theta and this is Q cos theta. Until this point it is P. Then you will be able to find out the resultant. Let us see if this is O and this is A and this is B and this C. Then OC square is equal to OB square plus BC square. And from this principle, you will be able to find out this length OC. Got it? You note down this. I'm going to derive that formula. This is all the fundamentals, right? So, depending upon this understanding only, you will be able to understand down the line the statics. That's why actually I am giving more importance for this, though it is a little lower standard than UPSC. Done? Okay. So almost 70 to 80% of these things are known already, but remaining 20% also is a must to understand the statics. That's why actually I am covering all these things. Now, from there actually, so R square is equal to P plus Q cos theta whole square plus Q sin theta whole square. So this will be P square plus Q square cos square theta plus 2PQ cos theta plus Q square sin square theta. And this is equal to P square plus and Q square cos square theta and Q square sin square theta will come to be Q square plus 2PQ cos theta. And this will be R square, which is nothing but the resultant. R is the resultant. And similarly, the direction alpha is equal to, so from there actually tan alpha is equal to vertical side is Q sin theta divided by horizontal side is P plus Q cos theta. Or alpha is equal to tan inverse of Q sin theta by P plus Q cos theta. So this is the angle. So this is how actually you will be able to find out the addition of the vectors with the help of parallelogram law of vector addition. This is P and this is Q. This angle is theta. So parallelogram you complete like this and draw the line like this. You will be able to find out this R vector. And then how do we calculate the subtraction of the vectors? How do we calculate the subtraction of the vectors? So change the direction of Q. Suppose if you want to calculate P minus Q, then this has to be change the direction, again add the vectors. That is P plus. That means you are again adding the vectors with the help of parallelogram law, but for the vector minus Q rather than Q. So that's why this will be, this is P, you keep as it is, and this Q actually in the upward direction, you treat this as the negative direction as minus Q. Then again apply the parallelogram law and then try to add these two vectors together. This will be P minus Q and this is P plus Q. Got it? So this is P plus Q and this is P minus Q. So here actually we say that the subtraction is a redundant because we already learned P plus Q. So P minus Q is no need to learn because you can straight away use P plus of minus Q. Now if you substitute here, then actually, so this angle theta, if you notice, this is pi minus theta. Because if this angle is theta and a straight line will make 180 degrees. So 180 minus theta will be this angle. Now in this equation, the magnitudes are same, only theta is becoming pi minus theta. Hence, in P minus Q, mod if you want to calculate, it will be P square plus Q square plus 2PQ times of cos of pi minus theta. Cos pi minus theta is minus cos theta. So P square plus Q square minus 2PQ cos theta. So this is P minus Q mod, right? So this is how actually you will be calculating addition and subtraction of the vectors. You note down this. Done? Okay. Now, triangular law of vector addition. So what this triangular law of vector addition says is, if there are two different vectors, earlier actually the second vector is joined at this particular location, or the tail of the second vector is joined at this location. In triangular law of vector addition, what it says is, rather than joining here, you join at the head of the first vector. So this is P and this is Q. Then this line starting from origin to the end point, if you draw a line, this will give the resultant magnitude. This is what is called as the triangular law of vector addition. If you want to add any two different vectors P and Q, so at the head of the first vector join the tail of the second vector, and then starting from this location to the end location, if you draw a vector, this will represent the direction and magnitude of these two vectors together. Now actually straight away this way, right? So it may not be very much useful for us, but actually especially when we are dealing with electrostatics, this kind of understanding is very much needed. Now actually in our case of statics, the methodology what we are going to use for this triangular law of vector addition is, there is something called Lami's theorem. So Lami's theorem actually, it talks about the vectors when those are in the equilibrium condition. So if three forces under equilibrium condition, you can apply Lami's theorem. Now those three forces actually, as per the triangular law of vector addition, whether the system is stable or not, or actually, so you will be able to find out with the help of triangular law of vector addition. Now I will show you how it is. See this, suppose if I have three different vectors joining a triangle, suppose this is one vector and this is another vector and this is another vector. Now if you notice, this is P and this is Q and this is R. Now as per the triangular law of vector addition, P plus Q, obviously it has to be equal to this vector, but this R vector is in the opposite direction. That means this is equal to minus R, right? Obviously P plus Q plus R equal to 0. That means if three vectors, if you join at the head of the one vector, the tail of the another vector, that way actually if you join all the three vectors, if it is a closed triangle, then we can conclude that those three vectors are forming an equilibrium system, equilibrium of forces. So all the three forces together are equilibrium. Now the same thing even be extended for the polygon law of vector addition. So suppose if there are multiple vectors, let us say this is one vector, this is another vector, and this is another vector, and this is another vector, and suppose if I have this vector like this, now this is P and this is Q and this is R, this is S and this is T. Now all the vectors together, so one head, another tail, if it is joined together, then if it is forming a closed polygon, then all the vectors together will form a equilibrium. So that means P plus Q plus R plus S plus T equal to 0. Or other way, suppose if you want to find out the sum of all the vectors, suppose if I have the system of vectors like this, so P, Q, R, S, then the sum of all the vectors together will be straight away joining the line like this. So this is, let us say Z, let us say this vector, Z is equal to P plus Q plus R plus S. So starting from the origin to the end point, if you draw a straight line, this will give the resultant. Got it? So this is what is called as the polygon law of vector addition. In that, triangular law of vector addition is a subset. Now here, if three systems, so three forces together forms an equilibrium, then we can apply, there is something called Lami's theorem. I am going to deal with once I am done with the multiplication of the vectors. So you note down this. This is Polygon's law of vector addition. Then okay. Now multiplication of the vectors. So there are two different kinds of multiplications. One is the dot product, another is the cross product. Now the dot product is, this is also called as the scalar product. Right? So why do we call this as a scalar product? Why do we call this as a scalar product? So resultant doesn't have direction. Why? So when we are multiplying with two different vectors, right? So the resultant, how can it be a scalar when we are multiplying two different vectors altogether? So multiplication of two scalars is no more giving us a vector, right? But multiplication of two vectors can be a scalar or can be a vector. Why there is a possibility of coming out to be a scalar? Now let me give the example. See this. Suppose if I have a block like this. On this block, now actually I have applied a force like this. And then let us say this is ground. Now on this ground, this body actually will try to move in this particular direction. And let us say this is the displacement direction, D vector. And this is the force vector. Now, as I explained in the previous class, work is nothing but the product of the displacement and the force. Why we have to consider both the vectors is, so to justify whether the person has done more work or less work, there are two important quantities that are needed. How much force that is needed to complete that work, that is one aspect. And another aspect is how much distance he moved. Because in every work, whatever you do, obviously there are two different fundamental quantities that has to be there always. One is the how much force that is needed to complete that work. Another is how much distance it has to be moved. Both are needed. And every force will have an effect of displacement. Now, force and displacement are equally important to calculate the work. So that's why, so in a logical manner, it was concluded that the product of the force and displacement will give the work. So work is equal to force into displacement. Force into displacement is nothing but the work. Now here actually the force, right, though he applied in this particular direction and the displacement is moved in the horizontal direction because this is making a hurdle for the movement in the downward direction. Now here the essential component of the work actually that is used to move this particular body in the direction of D is only the horizontal component like this. Now if this is making an angle of theta, then obviously as per the component of the vector, the horizontal component will be f cos theta. Now f cos theta is the one component of the vector which is essential or which is the only component that is effective in moving this body in the direction of the displacement. Now when we are dealing with the work, right, force into displacement is modified now as effective force into displacement. Because whatever the force you apply, if it is of no use, then actually he has not done any work. Now actually, suppose if I apply the force in this direction, now even if I apply 100 newtons of the force, there won't be any movement of this particular body in this direction. That means even if you are applying 100 newtons of the force, I say that you have not done any work because there is no displacement that is happening on this. Even if you apply 100 newtons of the force, that is of completely a waste, right? So the effective force that is needed is important for us for the calculation of the work. Now, this is the effective force is F cos theta. Now, F cos theta into D. F cos theta into D is nothing but the product, which is nothing but the work. Here actually, this F cos theta, if I say that this is F1, and then ideally I can say that F1 dot D is nothing but F into D into cos theta, because here F1 dot D, F1 and D are both are on the same direction. So the angle between them is 0, F1 direction and D direction. But F1D is having an angle of theta. But F1 and D is not having any angle. That means you can straight away multiply these two. Now here it is F cos theta into D. You don't need to specify the direction. Why? Because see, F cos theta is also one direction, and exactly in the same direction D is also there. Now actually, when there are two different directions which are having the same direction, right? So this is also in the direction of D, and this is also in the horizontal direction. This is horizontal, this is horizontal. Then actually, why there is a need to specify two different directions? Because both are one and the same. That means there is no need to specify the direction, because when you are taking the cos theta factor, means it always comes in the other direction of the vector. So then there is no need of specifying the direction. Hence we say that it is a scalar, because a scalar quantity doesn't need any direction. So when you are treating the first vector, whose effect is always in the direction of the second vector, then there is no need to specify the first vector's direction, right? So hence the resultant will come as a scalar, because it doesn't need any direction. Got it? So that's exactly the reason work will be a scalar. Now here actually we are making the product. We are making the product, and the result is coming out to be a scalar. And that scalar is coming into picture only if you apply a factor of cos theta. But if you apply a factor of sin theta, then this is the component, that is F sin theta, and which is completely a waste component, because it's no way making this movement in the horizontal direction. Got it? So F sin theta is completely waste, and F cos theta is completely effective. And because of the cos theta factor, there is no need to find out, so there is no need to specify the direction explicitly. Both will be one and the same. Hence it becomes scalar. Where if the component is F sin theta is effective, then there is a need to specify the direction there. I am going to explain that case later. So I hope you understood a fair clarity on the dot product. Got it? Okay. So you can note down this dot product. Now actually, so that's exactly the reason work is a scalar. Though F is a vector and D is displacement is also a vector. You can note down this. Okay. Now actually, if we find out the cross product, or this is also called as a vector product. So cross product or vector product. Now actually, when there is a need to consider only the F sin theta factor, then actually this cross product comes into picture. Now actually I will give a best example. Now actually, let us say this is a door. So let us say this is a door. Now actually on this door, so this is actually the pivot and this is the door. Now actually I wanted to move this particular door. So this pivot is like this, and then the radius of the door is this one, R. Now if I want to move this particular door in this direction or inward direction, now the force, suppose if I apply the force in this direction, let us crossly like this. So I am applying the force cross like this. Now if I try to move in this direction, that is of no use, right? The component that will be used to move this particular door inward is the perpendicular component of the force to the board, right? So if I apply a perpendicular component of the force like this, then the door will move immediately inside, right? If I try to move horizontally like this, it won't move. If I try to move in this direction also, it won't move. If I give certain angle, then f sin theta factor only will be essential to move the door inside. Correct or not? Right? So this is how actually I applied the force. This is my force direction, like this. Now it is making an angle of theta with the radius. Now f sin theta will be a factor which is perpendicular to this door, and f cos theta is a factor which is parallel to this radius, and f cos theta is completely a waste because it's not moving the door inside. Right? So here f sin theta will be effective. So f sin theta will be effective. And also, like actually, how much work I have done here actually, there actually we have calculated the work. Now actually the movement of the movement force is nothing but a circular movement force, what we call as torque. Torque is a force equivalent in case of circular motion. Now torque is nothing but the twisting force. Twisting force, and this twisting force is more if I have more radius. That means if I apply the force here versus, let us say this is point A, I have applied the same force, and at point B I have applied the same force. Which is more effective? Same force if I apply at A versus B. Which is more effective to move the door? Obviously it will be B. That means as you increase the radius, the torque will be more. As I reduce the radius, the torque will be less, obviously. So torque is nothing but R cross F. Why R cross F is, if you increase the R, obviously the torque will be more. If you reduce the R, the torque will be less. That means torque is directly dependent on the radius. That is one important factor. And another factor is the torque is even dependent on the force, but to be specific, the effective force. So F is important, but F sin theta is the effective there, because F sin theta is the one which will try to move inside. So R cross F is defined as, so modulus of R, the magnitude of R and the magnitude of F, and the angle between them, that is F sin theta. So this is R direction, this is F direction, this angle is theta. Obviously F sin theta is the component of the force, F sin theta, which will be effective in moving the door inside. So that's exactly the reason torque actually we call this as R cross F. Now actually there is one more factor called n cap comes into picture. N cap is a unit vector which is parallel to both the vectors. In this case, R bar and F bar. So which is perpendicular, not parallel. Which is perpendicular to both R and F. Now actually why this n cap comes into picture? Now let me explain. Suppose if I apply the force in this direction, F sin theta will be effective in moving the door inside. The same force if I apply in the opposite direction outward like this, obviously this door will come in the opposite direction like this. That means there is a need to specify the direction in which direction this door is coming out or coming in, right? So the force magnitude is deciding in which direction this door has to be moved. Now here actually this vertical line which we call as the pivot line, and this is the one actually the axis of the rotation. This axis of the rotation is specified as the torque direction. Now with respect to this axis, if the door is moving in the inward, so that is anti-clockwise direction, then if you treat that as a positive, then if the door is moved outward, then actually it has to be a negative, right? The axis is reverse or otherwise, right? So that means you need to specify the direction there, in which direction this force actually moving this door, inward or outward, or the clockwise or the anti-clockwise. Clockwise if you treat as positive, then the anti-clockwise has to be negative. So there is a need to specify the direction there. Hence, obviously, you will be specifying the n cap vector. This n cap vector, if you notice, this is the radius vector, and this my hand is the force vector. Obviously, this vector which is perpendicular to both radius and my hand force. Got it? Understood or not? So that's the reason with respect to this vertical line, the door is moving. Hence, the direction of the torque we say that is n cap. Got it? So direction of the torque is different, direction of the force is different. Direction of the force in which we have applied the force, but the direction of the torque is nothing but with respect to which axis this door is moving. So that means this axis direction, which is upward direction, is treated as the torque direction, but the force direction is inward to the board. Got it or not? Understood? Or do you have any questions on this? Understood? Okay, great. So this is how actually a cross product always demands a direction which is perpendicular to both the vectors, and a dot product will always leads to a scalar product. So wherever cos theta is involved, it will come as a scalar product, and wherever sin theta is involved, it will come as a vector product. There, obviously, there has to be a vector with the associated resultant, which has to be perpendicular to both the vector r and f. And obviously, from this result, if you apply force inward versus outward, the directional difference of torque will be there. Hence, r cross f is not equal to f cross r, but it is equal to minus of f cross r. So this is one of the important and fundamental resultant in case of vector product. Got it? Note down this. Done? Okay. Now, so this is about the multiplication of the vectors. But division of the vectors is not there, or it's not even defined. Why? Because when you wanted to divide a vector, right? So we feel that the way we have defined the negative or the subtraction of the vectors as redundant, even the division of the vectors is also redundant. Suppose if I want to calculate P by Q vectors, right? Then I can multiply with a dot like this, and then this denominator you can somehow make as a scalar quantity by making a dot product. Got it? So once you make denominator as the dot product, then actually this will be a scalar value. So 1 by some scalar value, and the numerator may be a vector, may be a scalar, depending upon the type of magnitude you have it here, right? So this way, if you are able to make the denominator as a scalar value, then no need of dividing it with a vector, because you are already making this as a scalar value, right? By doing a dot product with some random vector, any of your own interest. So there is no need of identifying the division, because this is redundant, which you can make use of the multiplication itself for calculation of the vectors. Got it? Understood? So this is about the vectors. So there is no need to define the division of the vectors, because multiplication itself we can reuse even to calculate the divisions. And then the next one is the 3D vectors. So 3D vectors actually, so there is something called directional cosines. So why we call this as directional cosines is, so suppose if you want to define a vector in a 3D space, that means let us say there is a fan in the room, then left bottom corner if you treat as origin, then from there actually if you straight away draw a line to the fan, then that vector, let us say we call that as a radius vector r, and this r vector can be expressed as xi plus yj plus zk. So this is how actually you will be able to express this vector r. Now actually from the fundamental theorem of the magnitude, that is r bar can be treated as x square plus y square plus z square under root. So this can be justified in this manner. Suppose if I wanted to move to that particular fan location from the origin, then I have to travel along the x direction for a distance of x, and I have to travel along a y direction for a distance of y, and then I have to go top to the fan for a distance of z. That means I have to go x direction and then y direction and then z direction exactly in this direction. Now let us say fan is located at this location. Now here, if I have to travel to this location, this is x and this is y. Obviously, this distance is x square plus y square under root. And because this is f, as per the Pythagoras theorem, these two are perpendicular to each other. Hence, the hypotenuse will be square root of x square plus y square. Now, z is located at this height. So, from this location, it is a z. Now, if you notice this line, or my hand, if you notice like this is having an angle of 90 degrees again with this. And this 90 degrees and this height is z. Obviously, this is also a right angle triangle. And this is the hypotenuse from here to the fan location here. And this length is nothing but the radius vector r magnitude. And then, because it is again a perpendicular or the right angle triangle, obviously this length and then this z. So the magnitude r will be r square is equal to x square plus y square under root whole square plus z square. So this will be x square plus y square plus z square. This is equal to r square. From this actually you will be able to identify the magnitude of the vector is nothing but square root of x square plus y square plus z square. Even it is valid even in the 3D also, right? So this is the position vector. So xi plus yj plus zk is nothing but the position vector whose magnitude is given like this. But in case of position vector of 2D, you will be straight away calculate, see this, the position vector, let us say this is r is equal to xi plus yj. And here actually the magnitude of this is x square plus y square under root. But the direction of this is theta, which is given as tan inverse of y by x. So which will straight away specify the direction of this particular vector. Now, in case of 3D, how do we specify this direction? So here actually in case of 2D, you will be straight away giving the theta value and you are saying that the direction of the vector is in this particular direction. So which is with respect to the x-axis at an angle of theta. But how can you specify the direction of a three-dimensional vector? Can somebody give me the idea? How we can specify a three-dimensional vector direction? Magnitude I have calculated, but how can we specify the direction? Exactly, right? So as Anubhav given, right? So the direction with respect to all the three axes you need to be specifying it. Here actually it's not a simple thing like two-dimensional vector where you need to specify only one direction, then you will be able to identify the direction of this particular vector. But in case of 3D, the complexity goes a little high because three different directions are needed to specify the direction. Needed to uniquely identify the direction of the vector. So these three are nothing but the directional cosines. So what it means is, suppose I say that, suppose this is x-axis and this is y-axis and this is z-axis. Then if you want to identify this particular vector which is located at this location, let us say this is the vector. Now this vector is making an angle with respect to the x-axis and it is making an angle of alpha with respect to, this is beta with respect to y-axis and this is making an angle of z with respect to the angle of gamma with respect to the z-axis. Now all the three angles together you need to specify the direction of this particular vector. So this is where the fan is located in this particular room, let us say. Now this x-axis, y-axis and z-axis are having different angles for this particular vector. Obviously you try to imagine in the room where you are located. Left bottom corner you imagine as origin and then try to draw a line to the fan. Then obviously the bottom lines or the boundaries actually if you treat as x-axis, y-axis and z-axis, this is x and this is y and this is z-axis, then this vector which is drawn to the fan is making an angle with respect to x-axis, is making an angle with respect to y-axis and is making an angle with respect to the z-axis. Now all the three angles together needs to be specified to identify this unique direction of the vector. Now those three vectors are nothing but the directional cosines or the directional angles ideally. Now directional cosines, why we deal with is, see this, suppose if you project this vector onto the x-axis, then the x component of the vector is nothing but, if this length is r, obviously r cos alpha will be x. Similarly, r sin alpha will be y. Sorry, r cos beta. R cos beta will be y. And similarly, this one, so this length is nothing but z, which is given as r cos gamma. If you notice, everywhere actually we are treating only the cos values. No need of sin value, because that is a completely waste for us here. But here, cos theta and sin theta are two important quantities for us. But here, cos alpha, cos beta, cos gamma are needed to identify the unique direction here. With respect to x-axis, if you want to specify this vector, you say it is an angle of theta. With respect to y-axis, if you want to specify this vector, we say this is 90 minus theta, right? So here actually it's not that case. Cos alpha is the x component of the r, and cos beta is the y component of the r, and cos gamma is nothing but the z component of the r. So that's why if you want to specify the vector in 3D, you can specify this as r is equal to xi plus yj plus zk, or you can specify as r cos alpha into I plus r cos beta into j plus r cos gamma into k. So this is how actually a 3D vector you can specify it. Got it? R cos alpha into I plus r cos beta into j plus r cos gamma into k. So this is the r vector. Now, if you want to find out the magnitude of this, that is mod r equal to, so this is r is equal to, or mod r whole square is equal to r square is equal to, so this is nothing but r square cos square alpha plus r square cos square beta plus r square cos square gamma. Now r square r square r square r square will cancel out, and then cos square alpha plus cos square beta plus cos square gamma is equal to 1. This is one of the famous relations. Cos square alpha plus cos square beta plus cos square gamma equal to 1. So this is in case of 3D vectors. Got it? Yeah, you can note down this. Done? Okay. Now, when we are dealing with the dot product with this kind of vectors, let us say R1 is equal to 2i plus 3j plus 4k, and then R2 equal to 3i plus 4j plus 5k. Then if you want to calculate R1 dot with R2, then the way you need to calculate is 2i plus 3j plus 4k dot 3i plus 4j plus 5k. Then here actually 2 into 3 I dot I plus 2 into 4 I dot j plus 2 into 5 into I dot k. And then 3 into 3 j dot I plus 3 into 4 j dot j plus 3 into 5 to j dot k. Similarly, 4 into 3 into k dot I, 4 in 4 k dot j plus 4 into 5 k dot k. Now actually, what is the value of I dot I? It will be 1. What is the value of I dot j? It is 0. So here actually, why I dot I is equal to 1 is, so there is one unit vector in the direction of x, and there is one more vector in the direction of x only, whose magnitude is 1, and the dot product of these two is 1 into cos of angle between them is 0. So 1 into cos there is 1. But when we are dealing with any other vector, any other unit vector, I dot j or j dot k or k dot I or whatever it may be, then the angle between them is 90 degrees. Because I is the x direction and j is the y direction. The angle between them is 90 degrees. Hence, cos 90 will be 0. Hence, this will go off to 0. And then this will go off to 0. This will go off to 0. And this will go off to 0. And this will also 0. And this will also be 0. So, whatever the components I dot I, j dot j and k dot k will be valuable for us. Because whose magnitude with the vectors will be 1. So, this is 2 into 3 is 6. And 3 into 4 is 12. And 4 into 5 is 20. So the sum of all these three will be the final result. That's why when we are dealing with the dot product, so you will be dealing with only 2.3. So 2 into 3, 3 into 4 and 4 into 5. Directly you will be calculating it. Got it? Exactly in the similar manner, you can even calculate the cross product. R1 cross R2. But the cross product actually a little complicated if you want to go in this manner. Because I dot j is k. And I dot k is minus j. So that is how actually you need to follow the order I, j, k. This is the order you need to follow. If you cross product these two, then this will come. If you cross product with these two, then this one. So this is how it will come in a circular manner. But if the circle is in the opposite direction, the negative sign will come. So that's why it has lot of confusion in it. So there is a standard method to calculate the cross product. So that method will be I, j, k and then 2, 3, 4, 3, 4, 5. So this determinant value will be the directly the cross product value R1 cross R2. Got it? So this is how actually you will be calculating the cross product, because this method of straightaway multiplication will be a little complicated or it will be lot of confusing. Hence we will be using this method to find out the cross product. Got it? So this is about the basics of the vectors. Do you have any questions on this? No? Okay, great. Fine. So with this actually, I'd like to stop the class for today. So from tomorrow onwards, you will be prepared for 8 to 9:30. So I'll be starting the class at 8 itself. Fine? Yeah. So that's all for today. Yeah. Thank you. Yeah. Good night all.